Good morning. Welcome to the Mcity ABC test virtual demo. Thank you for taking the time to join us today. My name is Hui Pen, Director of Mcity at the University of Michigan. Mcity is a public-private partnership. Our mission is to advance transportation safety, sustainability, and accessibility for the benefits of the society. Since the very beginning of Mcity, we have focused on connected and automated vehicles. As you know, safety is the foundation before realizing many other potential benefits of AV. Today, we are demonstrating a test procedure to test highly automated vehicles, defined as level 4 by SAE. We think that this test needs to be done before their testing or deployment on public roads. We have already seen too many crashes related to the AV still under development. I'm joined today by Associate Director of Mcity, Greg McGuire.
Thanks, Wei. Good morning, everyone. Thanks for being here. Today's Mcity ABC test virtual demo is a series of presentations that will outline why we think this Mcity ABC test concept is needed, how we developed it, as well as how it can be executed. We'll talk about scoring the results of this test. We used Mcity research vehicles in place of commercial systems. We'll also talk about simulation and how and why we believe it plays such a critical role ahead of physical ABC tests. And finally, we'll talk about Mcity OS, a cloud-based framework that we developed here at Mcity. This tool allows AV developers to design and execute all of the scenarios that you'll see demonstrated today using nothing more than a web browser. Now, we hope you have questions. We know you will. Please enter them in the chat along with your name and affiliation as we go through. We'll answer them at the end of the program. We know it's not every day you get to watch YouTube at work, so we'll do our best to make this very much worth your while. Thanks. Back to you, Wei.
Okay, let's get started. Today's program is largely organized as why, what, how, so what, and now what. So in the first video, Greg will introduce why the Mcity ABC test is needed.
Mcity works in a variety of areas, from law to policy to engineering. We focus on pre-competitive research in transportation, pre-standards, things that can become standards in the future. We're here today to focus on the topic of automated vehicle testing, how specific test methodologies play a crucial role in informing the public, ensuring their trust, and simultaneously assisting industry and government in the deployment and adoption of AV technology, all while supporting their mandate to do so safely. The question of how safe is safe enough has circled automated vehicle technologies since the very earliest concepts decades ago. In fact, the very existence of AVs is based on the promise of reducing roadway deaths and injury, while also saving energy and increasing access to our transportation systems. Unfortunately, we're not having the success we should be in reducing deaths and injury on our roads. Recent National Safety Council data shows over 42,000 people died in motor vehicle crashes in 2020, which is up over 8% from the prior year, despite people driving less because of the COVID-19 pandemic. If automation is going to help us as one of the many tools in our toolbox to improve transportation safety, the technology first and foremost has to be trusted. Thought experiments in AV tech have quickly become human subject research on our roads as industry, as newcomers from outside the automotive industry and others have experimented with automated vehicle services and begun to transport people on public roads. Some are doing an excellent job of this safely. Others Likely not. It's hard for the public to tell without a clear, transparent window into those processes. In the wake of several fatal crashes early in 2018, understandably, consumer confidence and trust in automated vehicles and concepts plummeted. The optimism dampened about how AVs could help solve some of our society's thorniest transportation problems. This was understandably a jolt to the industry. I think some of the enthusiasm for AVs may have been born of hype, in fact, but the fatalities were an appropriate wake-up for us. The how safe is safe enough question then was joined by a how do you prove an AV is safe enough to operate on public roads? Enter Mcity's Automated Vehicle Working Group, which is comprised of our industry partners and academic researchers. They responded by kicking off research into testing techniques that could be used to both answer this question, as well as do so in a very publicly visible way. Mcity then developed what we call the Mcity ABC test concept for gauging the competency of automated vehicles in a controlled environment prior to testing moving onto the public roads. So now, several years after these fatalities, our National Highway Traffic Safety Administration, NHTSA, is exploring the idea of developing a safety framework for AVs, what they call automated driving systems. Only 14% of people who drive would trust an AV. So against that backdrop, we feel the Mcity ABC test could serve as a blueprint for developing a safety testing protocol for automated vehicles. Perhaps most importantly, it would be public and help show that a particular system can be trusted to safely use our roadways alongside us. Thanks. The Mcity ABC test concept was developed by Way in conjunction with many of our industry partners. In the next segment, Way will talk through a bit of the background around that development, as well as take you through the methodology for its execution. Let's watch.
Let me give you a little bit more details about the Mcity ABC test methodology. Why are we doing it and how do we do it? Like Greg said earlier, the few crashes that are happening in Arizona and California are not helping with the public confidence and public trust. We fully believe that AV can make ground mobility safer, cleaner, and more equitable. In the meantime, without the public trust and confidence, their full potential may not be realized as soon as they could. So let's look at the systematic way of designing AV and win public confidence and trust. Let's imagine the whole possible driving out there that someone needs to solve is this big red rectangle. Some may argue that this big rectangle is infinitely large and fuzzy because there are so many possible combinations. In the meantime, let me first introduce this concept of Operational Design Domain, also known as ODD. When we deploy the Level 4 shuttles in North Campus of the University of Michigan, we limit the speed to be 12 miles per hour. We don't operate in snow, and it has a fixed route. When the deployment of AV is geo-fenced, speed limited, weather limited, they have a well-defined ODD. So the ODD is this big red rectangle. So the job of the designers is to make sure that a bigger and bigger area of the red rectangle is shown to be safe. In the meantime, the job of the evaluators or verification validation guys or V&V guys are trying to show that a bigger and bigger portion of the red rectangle is known to be safe. These two functions are usually done by two different groups within a company, or the V&V function can be done by the government or a trusted third party. So how do we do the V&V part? We are proposing this Mcity ABC test concept. ABC has two meanings. Number one, we first think that this is a first step toward a systematic definition and methodology for V&V. Second, A actually stands for accelerated evaluation. Safety events are rare events. We know that there is only one fatal crash every 100 million miles and one police reported crash every 500,000 miles. Obviously, we don't have time to drive so many miles. Therefore, we have to do the evaluation in an accelerated fashion. B stands for behavior competence. We have built a library of 50 scenarios, and we obviously understand that not all 50 scenarios should be tested for every AV. In fact, the scenarios and test cases should be selected based on the ODD of the AV. Finally, corner cases, we must find a systematic way of testing at the boundary. In other words, cover the corner cases. We talked to many of the Mcity members. We have 60 industrial members. In addition, we talked to researchers all around the world, including Asan Sakura Project from Japan and Pegasus from Germany. We also work with a lot of researchers and read their papers all around the world. And most importantly, we compare notes about how naturalistic driving data look like. Obviously, the driving culture, behavior in China, Europe, and US are all very different. But after accumulating a lot of driving data and we compare our notes, we found that while the detailed parameters behavior may be slightly different, qualitatively they are all very similar. So here's a little bit more detail of how we cover the big red rectangle. Now the details is shown in this green ellipse. Out of all the real-world driving, we carve out the real-world driving into many blue ellipses, and only those blue ellipses falling within the ODD will be selected for testing. Our primary job is then to select the test case parameters so that the red ellipses are approaching those blue ellipses as much as we can, in other words, covering all the way to the boundary. And when we choose the test case parameters, we must ensure that they are done in an accelerated fashion and cover the corner cases. So the more detail of how we sample from those test case parameters are the following. Here are 4 example scenarios: pedestrian crossing, cutting, unprotected left turn, and car following. In short, we cover a lot of the naturalistic driving data. We build models, and we try to sample test case parameters from the model. The color in the last row of the table show how challenging the test cases are. Green means easy, yellow means medium, orange means hard. The red color shows impossible cases. Obviously, it's meaningless to test impossible to avoid cases in a test facility because we know the result is a crash. So today we are going to demonstrate 7 scenarios as examples for the Mcity ABC demo. So we'll be using the 3 test vehicles highlighted on the left-hand side. And the 7 scenarios are selected based on several considerations. Number 1, they are all from our 50 scenario library. Secondly, they contribute a lot to the challenging crashes, and human-driven statistics show that they are very important. And thirdly, we are using them to show that we can test even the more challenging test scenarios that are not easily to test. For example, for door opening, we are developing technologies that leverage the Mcity OS and the automatic testing functions that we have developed in order to show that we can do testing that many other places are not yet ready to do. So please enjoy our demo of these 7 scenarios.
In this example test loop, an ABC test car will encounter 7 different scenarios in a single loop. This test loop consists of 1. A highway merge. 2. A highway cut-in. 3. An opening door. 4. A deer in the road. 5. A crossing pedestrian. 6. An unprotected left turn. and 7. A roundabout merge. The test loop begins with the highway merge. The test car approaches the highway on an entry ramp. The challenge car remains in the right-hand lane, preventing the test car from immediately merging. A successful test would involve the test vehicle slowing down or coming to a smooth stop before safely merging, preventing the test vehicle from hitting the challenge vehicle. In the second scenario, the highway cut-in, the challenge vehicle approaches the test vehicle from the left and abruptly cuts in front of the test vehicle. A successful test would involve quickly slowing the test vehicle down to avoid hitting the challenge vehicle. Next, for the opening door test, the test vehicle approaches a stationary challenge vehicle from the left. The challenge vehicle's door opens abruptly into the test vehicle's path. A successful test would involve the test vehicle successfully swerving to avoid hitting the open door of the challenge vehicle. The fourth challenge places an obstruction in the form of a deer on a blind curve on the right-hand side of the road, directly in the path of the test vehicle. A successful test would involve the test vehicle slowing down and proceeding cautiously. For the next scenario, the crossing pedestrian, a mobile robotic platform representing a pedestrian abruptly moves onto the street into the path of the test vehicle. A successful test would involve bringing the test vehicle to a smooth stop, preventing the test vehicle from hitting the pedestrian. In the sixth scenario, the unprotected left turn, the test vehicle approaches an intersection. From the opposite direction, the challenge vehicle makes a left turn directly into the path of the test vehicle. A successful test would involve bringing the test vehicle to a smooth stop, preventing the test vehicle from hitting the challenge vehicle. For the final challenge, the roundabout merge, the test vehicle enters a roundabout. As it circles around, the challenge vehicle enters the roundabout, merging suddenly in front of the test vehicle. A successful test would involve the test vehicle slowing down or coming to a smooth stop, allowing the challenge vehicle to safely merge and preventing the test vehicle from hitting the challenge vehicle.
MCT ABC test concept can be used as a blueprint for standardized testing for AVs, perhaps resulting in a safety and roadmanship score. What might that look like? Let's take a look. So let's talk about the concept of scoring. After every test, we must judge whether the vehicle passed the test or not and whether it is receiving a nice score. Obviously, scoring is the job of the government or government endorsed third party, but we're going to talk about the concept. The important concept is being safe is not enough. For example, in this particular video, you can see there's no crash. In the meantime, the vehicle applied hard braking, which is causing trouble for the car behind. So obviously, crash means fail. In this particular animation, you can see that the vehicle crashed into the pedestrian, which means it fails the test. But even if there's no crash, there may be several reasons we don't believe it is a perfect execution of the scenario. For example, the vehicle can brake too hard, stop too far away, and that's not acceptable. Or another example is that the vehicle comes too close to a pedestrian, that's not acceptable either. Finally, even if there's no other problem, but the vehicle was weaving around and having strange steering behavior, that's also not acceptable. So after every test, if there is crash, obviously the vehicle will not receive any score. Otherwise, we will be judging its score based on several considerations, including efficiency, meaning the vehicle has to drive fast enough. Compliance means the vehicle cannot violate any traffic rules. Past tracking, it couldn't weave around too much. And finally, smoothness. Nice steering and without unnecessary hard braking is necessary. Simulations are an important tool for the AV development and testing. You can use simulations to develop the ABC test capabilities first before deployment in a closed track. Mcity has been using simulations a lot in our development and testing. Let's take a look at how simulations are used by Mcity. Like many other AV researchers, we also do simulations because simulations are safer, cheaper, and faster. We work with many of the Mcity members and non-members to create virtual Mcity. Today, 8 commercial and 2 open source software has a version of virtual Mcity. Some of them produce photorealistic Mcity, some of them has virtual reality Mcity, driving simulator Mcity, and Mcity simulation for detailed sensing perception algorithm development. We have been doing a lot of simulations in the virtual Mcity. This is a Kala version of Mcity. This is maneuvers similar to what we are demonstrating today for the ABC test. Obviously, we do a lot of this development in simulations first before the algorithms are put into our test vehicles for real vehicle test demo. So especially scenarios that involve vulnerable road users and unprotected left turn, which are having a high risk of crash, we'll be doing a lot of these simulations before lab testing. Of course, lab testing we think should also go before real-world deployment. One of the critical missions of University of Michigan is education. We work on 2 open source simulation software because they are widely available to students. Kala, Sumo are both open source. The softwares have been used by both researchers at the University of Michigan as well as from other universities such as MIT, Stanford, and University of Washington, St. Louis. We offer this simulation available to other students in the world.
Critical. Now, Mcity has developed a library of 50 logical scenarios that can be evaluated using the Mcity ABC test concept. Producing reliable results for these tests requires setting testing parameters that can be reliably reproduced, that are highly repeatable. Mcity OS then was developed as a framework that allows AV developers to quickly design and execute these sorts of tests with a high degree of repeatability and variability as needed for a particular test. Let's see how it works. If we're going to realize the promise of AVs, we have a challenge. The simulation and track tests of today's driver assistance technologies will need to become magnitudes more capable. Scenarios that accurately represent challenging real-world conditions can quickly balloon in complexity. As you can imagine, coordinating all of the systems involved in even one scenario is quite complex, let alone repeating them or chaining them together into a fluid system. Having to do this coordination manually would add not only significant time, but we would struggle to achieve the repeatability of timing and position that we need to be able to measure and score the results accurately. Individual intelligence needs to be integrated into a single orchestrated system. To solve this, we created a framework we call Mcity OS. Mcity OS is a cloud-based tool we've developed that lets you create and execute complex AV test scenarios using an app on your laptop or smart device. Think of Mcity OS as the nerve center for the Mcity test facility, or for any test facility. It is able to understand the location and motion of everything, including the vehicle we want to test, and coordinate responses at the right time and in the right place. You can write scenarios in a graphical tool we've built called Skyline and load them into Mcity OS. To make Mcity OS aware of the vehicle we're testing, No complex instrumentation is required. Simply attach our positioning hardware to the outside of the vehicle and power it on. Frameworks like Mcity OS play a critical and supporting role in carrying out the validation and verification tests on AVs as they become capable of handling the role of driving safety.
Okay, that wraps up today's demonstration. Let's talk about what should come next. While we think that,
I'm showing the slide right now.
okay. All right, so let's talk about what should come next. While we think we have a good concept, it's still far away from being able to do reliable, repeatable testing 24/7 and produce reliable results. It's almost like having the concept of a new mRNA vaccination concept, but still scaling up the production to high quality shots and being able to come up with cold supply chain, distribute to many states or many countries in the world. A lot more work needs to be done. So we are calling the help from others, including everyone on this streaming event, that we need to go from concept to blueprint to fully finalize standard testing and to be able to execute this testing so that before AV are deployed on public roads, they are fully tested and people are trusting that they are safe. So now we are ready to take your questions.
Thanks, Wei. Absolutely agree. All right, let me check on our questions here and see what we've got from the audience. As a reminder, if you have them, please enter them in the chat along with your name and affiliation, and they will eventually come through the interwebs to me here in the studio. Wei, we have one question. Are the 50 scenarios given viewed as a comprehensive, complete set of tests or just as a starting point?
While we have already talked to many people and we have consulted many research groups and tried to make sure that we review all the scenarios people talk about that they are very challenging or commonly experienced on public roads, they are by no means complete. We are certainly looking at this library as a starting point, and the number is likely to grow. But again, the idea is that not every AV need to be tested with all the scenarios in the library. For example, if for our Navia shuttle deployment at Mcity, our top speed is only 12, we don't have any roundabout, and so on and so forth. Therefore, not all the 50 scenarios are relevant to all AVs. So again, the library will grow, but it's important to remember not all scenarios need to be tested for every AV.
So it's a selection process.
It's a selection process.
Understood. Mm-hmm. So maybe a follow-on to that from the audience. Examples are given where it seems the data is known for impossible, hard, moderate, easy, and so on, in the graph that you showed. Are these data known for all the scenarios or just the ones that we've talked about today? What's missing?
Yeah, that's a great question. So today, many groups, many researchers have collected hundreds of millions of miles of driving. There are a lot of open source data out there. In the meantime, have we analyzed the data for all the 50 scenarios? The answer is no, because some of the scenarios are relatively rare, like encountering an animal, maybe a deer or kangaroo. We don't believe we have enough data to capture the encounters with animals, and therefore building a so-called naturalistic driving data statistical model is not easy for all 50 scenarios. They are all very different. Some of them are very common, some of them are less so. So I should say that the concept of 50 scenarios are there. do we have enough data? Do we have all models for all of them? That's not necessarily true. However, but let me point out to one thing. The idea of whether a challenge test case is hard, medium, or easy, or impossible, those can be actually analyzed by so-called controlled reachability analysis. For example, if a pedestrian suddenly jumps in front of a car, there may not be enough friction, tire friction, to stop the car in time. Therefore, there are definitely always impossible cases for all the 50 scenarios. And the level of challenge is largely determined by controlled reachability analysis, meaning by analyzing the capability, how hard the vehicle need to brake or swerve to avoid an accident. So the fundamental analysis is there, the data is not necessarily there.
All right, thank you. Let's see. Maybe one that I can answer. How does Mcity ensure repeatability of the tests? I'll start, and then maybe I'll toss it to you, Wei. I think this is exactly the reason why we built this Mcity OS framework. You know, when you have these vehicles of extremely high capabilities that are responsible for the driving safety task, a tremendous amount of automation, you know, you can't be running those through a series of tests where there is human variability, say, in the tests themselves. And so, you know, Mcity OS then, we built it so that you could control lots of different actions happening in a particular scenario, in a complex scenario, in orchestration, and do that repeatably. So, you know, I think from Wei's point previously, perhaps let's take one of the variables like a time to collision or something, you know, based on what that number is, gives you your sort of easy, medium, and hard, but that number you may want to vary that quite a bit so that there's some randomness in the ABC test, and it's not a known set of static tests. To be able to do that, though, you want to be able to set that time and then have that repeat, so the traffic signal, you know, turns yellow at the same time that you know, my pedestrian proxy begins to cross the road, as we saw. Doing those things with a high degree of repeatability requires orchestration, and that's really the concept behind Mcity OS. That's what it was developed to do. It sits outside the car. You know, it controls and understands the position and action and state of everything that's happening in our test facility. And it's our hope that that can get picked up and used as a concept by industry or beyond. Wei, anything you want to add on that?
Yes, great. Indeed, Mcity is the backbone of ensuring that the tests are repeatable, reliable, accurate. Other than the operating system, we also need to make sure that all the road players, for example, door opening, you need to detect the incoming vehicle position and then send that triggering information to pop open the door. When you want to encounter a left turn or cutting vehicle, you need to coordinate and make sure that the position and so forth, everything is known and repeatable, reliably executed. The reason we are using 3 MKs, if you notice, is that number one, these are real vehicles, so their dynamic characteristics are similar to what you will actually see out there on the public roads. In the meantime, we have the steering, braking, throttle, even gear selection is automated, and we have RTK, real-time kinetics, measurement, in other words, 1" to 2 accuracy. Therefore, we are guaranteeing that if we are measuring the position and control the velocity, acceleration of all the road players reliably, the tests will be executed accurately, reliably, repeatably, with the help of Mcity OS coordinating all the players. Great,
thank you. I think obviously, I agree since we've worked on this together. We used an Mcity vehicle as the stand-in for potentially a commercial system. Now Mcity is largely focused on research and in the pre-competitive realm in areas like this where we think there's a need for across industry, across society. But I think we've got a question here about the Mcity, the vehicle that was used, that was challenged in the test. Do you anticipate, what's sort of the next step then for that? We take that vehicle out, and what do we do? How do we demonstrate this, in our next incarnation?
Yes, great. That's a great question.
Yeah.
So obviously today we're using 3 MKZs owned by Mcity or owned by Denso.
Right.
So we are able to control all the players they are all collaborative. They help each other and so forth. So what's the next step is really to replace the vehicle being challenged with a AV that are being developed by a company or research group. And then we can make sure that there's no cheating, right? They are not really collaborative. There are certain things that will be triggered, but there will be certain things that we do not know. So
Yes.
obviously, when we want to do some of this testing repeatably, we probably need to stick a RTK on the roof of the vehicle we are testing.
Right.
For example, from a OEM. Other than that, there really doesn't need to be any. Our OEM, our RTK come with communication too, right? So it will send the position information to all the other players so that they are challenging the AV at the right time, at the right place, with the right relative speed and so forth. Other than that, there will be no collaboration among the players. So that will be a very nice next step for our Mcity ABC test.
That's great. So you're saying, I mean, we really developed this test such that it doesn't need intensive instrumentation of the vehicle to be challenged. We can kind of bring that in, and the whole system works around it.
Yeah, we have manufactured 10 POCs, as you know, Greg.
Yeah,
You led that effort.
Yeah.
We will stick a POC on the top roof of the vehicle that's coming into Mcity, and that's it. So there's no anything else that
Right.
need to be done.
Right. Thanks, Wei. Let's see, another question from the audience. This is a great one. May I know, how do you ensure simulation fidelity? Do you compare the result between the simulation and the physical tests? How do you bridge that gap between the virtual and the real?
That's a great question.
That is a great question.
I will begin by saying the reason we work with 8 commercial softwares and we asked all of them to build a virtual MCT is we always convince them that, look, there is a real MCT, there is your digital twin MCT, and how to make sure that your simulation tool is believable and it is a good replacement of the real testing. It's really up to the commercial software, our partners, to make sure that's happening. At Mcity, of course, again, we are part of the University of Michigan. Simulations are largely an educational tool. We want to make sure that our students are exposed to both the state-of-the-art simulations and testing capabilities.
Yeah.
So trying to coordinate between our Kala model or Sumo model with the real MCT wasn't really the key. The key, I think, that we were hoping our partners, our industrial partners, are doing that, and make sure that they are impacting the industrial practice and make sure that simulations can be a safer, cheaper, faster alternative to real testing.
Right. So, because, Mcity, we're not in the business of building a better simulator, but we do want industry to succeed here. And so being able to compare our physical test facility with the virtual ones that they've built is a really critical piece of work for us,
right,
now and in the future. Okay, thanks. That was from Sean Zhang, by the way. Let me see if we've got other questions. So can multiple vehicles run tests in parallel in order to reduce total testing time, or is only one test possible at a time on the track? And I think maybe people don't realize because we didn't do like a Alfred Hitchcock 12-minute take on that, but that test, the 7 scenarios were done in one loop, right? There was no stopping in between. That was a single test.
Yeah, so indeed, I think the reason we choose those 7 scenarios because they are very important, they are common, and they can be grouped into one loop, and we can finish all the 7 scenarios in about 3 minutes.
Yeah.
So there is some kind of design, right? We want to make sure that this is the sequence of this big loop. So the AV comes in, they run 3 minutes, and they were challenged by the 7 scenarios one time each, right, within 3 minutes.
Yeah.
So that's efficient. Now, Mcity is really small, right? If you haven't come to Mcity, you see that it's already crowded somewhat.
It feels big to me, but you're right. You're right.
We need to worry about safety, encroachment, and so
Sure.
forth. So everything is carefully designed. Imagining 2 vehicles inside Mcity, it's a little bit crowded, but certainly there are much bigger facilities like ACM, TRC, and so forth.
Yeah.
Mcity is really not a commercial entity. We are researchers. We developed the concept, and we are waiting for others to help us to scale up. Like, again, mRNA vaccination.
Right.
We come up with the concept. Doesn't mean we are the ones scaling up.
Right, right. So we're just here to showcase the techniques, help develop them, and then see them off,
Right.
like sending our kindergartner to school for the first
Right,
time.
exactly.
Right.
Yeah.
Thanks, Wei. There's let's see, a question from Timothy Otaken. In the examples, it looked like typically there's a single test and a single challenge vehicle. Are there currently scenarios where there are multiple challenge vehicles to create tighter constraints? And maybe I'll say first, some of those scenarios do involve multiple actions where, for example, the traffic lights, the crosswalk timers, the pedestrian proxy, those things are synchronized. But Wei, maybe you'd like to talk a little bit about what happens when there are multiple vehicle actors, or a pedestrian plus a vehicle, or things like that. How do we handle that?
Yeah, that's a great question, Greg. I think that comes back to the fundamental philosophy of believing you should replay the most dangerous scenarios you collected after 10 million miles of driving, and you look at those real-world encounters, and you say, these are the 50 most dangerous trips, let's replay those 50 trips. Or you say, let's decompose driving into behavior competence. Each time there's only one factor being varied. For example, we worry about cutting in combination with sharp curve, in combination with a steep uphill, and occlusion, and so on and so forth. The answer is no. The reason is very easy, right? If you say, if we assume there are 50 basic scenarios, and then you start to thinking about the combination of scenarios. So again, sharp curves, steep uphill, snow, occlusion, and so on and so forth. You start to really have exponential growth of the number of testing you need to do. Obviously, for companies, they probably need to think about this, beyond behavior competence scenarios. But that's imagine, right? There's a government-mandated testing or entrusted third-party testing. They only have weeks or at most maybe a couple of months, not years and years to do this testing. So therefore, it is very important to consider these are just behavior competence with simple scenarios, not infinite combinations of all the varying factors.
Right.
Yeah.
Thanks, Wei. I think that said, I could imagine we had safety drivers obviously involved in ours, and we had relatively safe time margins in the demonstration. But, I could imagine a time when these tests are being executed by the system, and there aren't necessarily humans sitting in the vehicles, right? So you could work your way up to some fairly high speed or potentially risky tests but in a place where there are no humans involved, even test engineers, right?
Yeah, so we are just a poor university. Each MCAS is $300,000.
Right.
Therefore, we always have a safety driver. But when we scale up, certainly we can imagine that, number one, you never test impossible cases, right?
Right.
You want to make
Right.
sure that all the test cases are avoidable, and you start by testing the easy cases. And only when the vehicle passed the easy cases, you move on to medium and move on to hard.
Okay.
You don't push all the way to hard in the first
In the
trial.
first, yeah. Which is
So
what
in
we
a
do.
commercial scaling up, I could imagine a future when they plan everything carefully. You will not need a safety driver. Everything can be robot controlled, Mcity OS controlled, and then you can do 24/7, things like that.
Yeah.
That, again, scaling up versus a concept is very different.
Thanks, Wei. I should note that we were very cautious in the development of our scenarios, as Wei just said.
Because of budget limitation.
Yes, well, and of course, the safety of our graduate students who, are obviously is critical. Let's see. Are there plans? This is from Scott Popel. Are there plans to expand naturalistic driving studies done for more of the scenarios? Understanding the simple to challenging to impossible, backed up by real-world data, is most valuable for industry, he says. Perhaps, Wei, this is a time to talk a little bit about our plans in the next 3 years for some of the infrastructure data collection or those kinds of opportunities.
Right, so let me talk a little bit about how do we sample the test cases. Obviously, we talk about going from naturalistic data to models, and then we sample from the models. Now remember that when we sample from the models, we say, these are the easy cases, but easy cases, you see a bend, right? The reason we are advocating for a bend is we don't want deterministic, pre-announced test cases only. We believe to avoid people only prepare for the test or actually cheating in the tests, it's very important that there is a stochastic element in our test. That's why there is a bend. So when you sample from, say, the green or yellow or orange regions, you sample based on the model you built, based on naturalistic data. In other words, those are actually happening out there in the real world. Why? Because, again, you are using this test to replace driving on public roads, but you want to do it in an accelerated fashion, right? You don't want to do 10 million miles of driving. You want to finish seeing many of the medium and hard cases, which, by the way, are relatively rare out there on the public roads. So by sampling your cases in a smart way, you achieve accelerated evaluation, and you sample based on the model you built from naturalistic data.
Okay. So how do we go about filling in those gaps? Is that something that Mcity plans to do? I happen to know the answer is yes. I don't know if you want to...
Yeah, so when we do, but also we call for help.
Yeah.
Right? So obviously, any single entity would not have enough data to build enough naturalistic driving trips to build the models we need. Therefore, we are calling for help. We actually need to make sure that we can collect as many miles as possible. In particular, let's say we have a challenge of, let's say, roundabout.
Okay.
And there are not too many roundabout trips out there. And there are not too many kangaroo jumping trips out there. For example, I'm just joking. But the idea is that you never have enough data. And that the first thing first, we need to help to get some help is to make sure that we have enough data to make sure we can sample and build models for these 50 scenarios.
Right. And I think being able to collect that data while being cognizant of residents' privacy or people using our roads, expectations of privacy and things, those that becomes a bit of a balancing act, doesn't it?
Mm-hmm. It is.
Yeah. Okay. Let's see. We've got one sort of wide open question. What do you think is the biggest challenge in the autonomous driving field? Maybe I'll start there,
Yeah.
and then you can
Yeah.
think about
Mhm.
it.
Yes, good idea.
Yeah, I think I think public trust and value to society are sort of two of the biggest, in my opinion. Can these automated driving systems, these systems where the driving safety task is, belongs to the vehicle systems, to the software and hardware that's running the vehicle, can that be valuable to society more broadly? Will that help us improve our reach of public transit? Will that help us reduce congestion, improve safety, those sorts of things? Those are, I think, all promises, but how are we going to get there, and how are we going to get there safely? To me, I think are some of the biggest challenges. I think that it's not without precedent. I know it's not an entirely fair comparison, but the airline industry, has certainly improved its safety record tremendously over the last several decades. So we know it can be done, and I know that there's commitment, from Mcity as a public-private partnership. We have government, industry, academia. I know that there's commitment there from all three. So I think that's my answer. Wei, what do you think?
Yeah, great. I think public trust is very important. It's
Yeah.
important to remember that we are doing this research because we want to make ground mobility safer, more sustainable and more equitable. So it's really what benefits the society is more important. When people don't trust AV, nothing will happen, right? So it's important to remember the time from Charles Lindbergh flew across the Atlantic Ocean to the time people trust their lives to a flying bird. It takes several decades.
Yeah.
So now most people don't even think before they buy a ticket to fly to Florida.
Yeah.
So we are not there yet.
Yeah.
And it's important to start from ODD that you can do it, and you are not a cavalier in thinking that as long as I sell a product, I make some money, I'm fine. You should clearly declare or disable your AV function when you know it's not safe to do so. For example, in the past, people could drive a, say, level 1, level 2 vehicle at very high speed, perhaps higher than what the engineers actually feel comfortable. I think it's important we start by everybody know that it's not abnormal to have an ODD. Limit your top speed of, for example, the autopilot now limit to 75 miles per hour.
Right.
I think that's a great starting point. Super Cruise from GM limit the driving system can be enabled only in those, say, 200,000 miles of highway environment. Those are great points to start. We need to be careful. We need to build trust with time. When people have seen that this low-speed shuttle running around, starting from 12 miles per hour to 15 to 20, and they never cause any problem, safety and roadmanship-wise, they will gradually build their trust. So I think that public trust is definitely a huge bottleneck. Of course, technically there are reliable perception, high cost, there are many other issues, all of which are, in my mind, easier to solve because those are well-defined. Public trust is an ill-defined problem.
But critical.
But
else we're missing the point.
Right.
Yeah.
Yeah.
Thanks. How, let's see, we've got a follow-up from Sean Zhang. how do you select the parameters for corner cases, for concrete corner
Yeah,
cases?
exactly. So again, the idea of saying we never test impossible cases literally basically says anybody can jump right in front of your car, or they are just impossible test cases.
Yeah.
And we don't want to test those because it's meaningless.
Yeah.
No AV can guarantee no crash, because crash is a two-party tango. You can't really control what the other party does on public roads, but that doesn't mean you shouldn't control the other party in your test cases, right? So we never test impossible to avoid cases.
Somebody crosses the double yellow, say, with not enough time for the friction.
Head-on crash is a common example, right?
Yeah.
So on a divided, so let's say the road with the double yellow line. The other party cross the double yellow, what can you do? Very little, right? So you can easily come up with impossible test cases for almost every scenario.
Yeah.
Should you choose those? No.
Right.
But should you define a boundary? You are basically saying, if friction limit is 0.6 and I allow you to have some delay in communication detection, computation delay, and then you apply maximum braking, you should be able to avoid this one. So you want to make sure that you draw the boundary, and then you sample your test cases all the way to the boundary. So the boundary defines something that is very hard, but avoidable.
So I think it's probably worth mentioning, there's others. We're obviously not doing this development in a vacuum. There's others at the University of Michigan even, Professor Henry Liu, who's working on some corner case testing. There's some startups in our ecosystem like Deepin, who are doing that as well. I can think of some other commercial folks, Edge Case Research and things.
And all the leadership circle members participating in our discussion,
right.
Many of whom are active in SAE, ORAD, or other organization defining the standards, and they have a rich set of knowledge, and they contribute significantly to the definition of the ABC test.
Right. Thanks, Wei. Yeah, I think that's the most valuable thing in my mind to the consortia approach that we have, which is, it brings in groups and a variety of really unique stakeholders that provide a lot of diversity in thought, which I think has been very helpful for us. So thanks out to our Mcity member companies especially for supporting us in production of this and the development and research behind these things, which was significant. Wei, I know we're close to time, so I think I'm gonna wrap us up here if you're all right. Do you have anything you'd like to close with, or shall I?
Oh, you can do it.
All right.
Yeah.
You got it. So I just want to thank everyone for watching today. We sincerely appreciate your support. I think, as Wei mentioned, we've got a lot of next steps. We are a relatively modest group at the University of Michigan, and so the next steps will take cooperation from you, your input, development, and I thank you in advance for it, and thanks for participating today. I know Wei and I sincerely appreciate it, as does the whole team here at Mcity. On behalf of Mcity, the University of Michigan, all of our member companies and partners, thanks for tuning in today. You can find more information about Mcity, as well as this ABC test concept that we presented today, on our website, which is mcity, M-C-I-T-Y, shockingly, .umich, umich.edu, mcity.umich.edu. All right, thanks very much for your time. Take care.